Good morning. I guess that makes us the warm-up act. As it's a slightly contentious subject, if people aren't getting slightly heated by the end of it, then we're not working properly.
Right. Very good morning, everyone. I'll leave David under the supervision of Jan, and I shall try to gallop quickly through the prepared part of the presentation, and then throw it open to discussions with David, because those books there on the table are where the bodies are buried in the noise figure measurement equipment. Right. Amateur radio has a big problem that we don't have a collective memory in the way that professional academic electronics does, for example, where people publish papers, people teach, people come in to learn, and it builds up on what is already known. Amateur radio doesn't do that. Amateur radio learns things individually and patchily. We learn things on a need-to-know basis, and then maybe we forget. And every now and again, we need this reality check. That's what we would like to believe. That is more like the truth. So let's examine that. Noise figure errors, the earliest reference we can find is something published in 1961 by what was then Airborne Instruments Lab, which became AILTech. And already it was becoming something of a joke that you could, if you know enough about it, you can manipulate the errors in noise figure measurements to get any kind of result you want. And yeah, it was meant as a joke. That means by 1961 there were supposed to be people who already knew this and could join in the joke. But 50 years later, the same mistakes are still happening. And that's the sad thing. Since the 1980s, we have certainly known about this in detail, and the articles that have been most accessible to us have been by Rainer DJ9BV, who, those of you who knew him will know that any subject area that Rainer touched became better, and noise figure was certainly one of those. But again, we've forgotten. It still doesn't work. The other thing is the human factor. We wish that we didn't have to know about these errors. We wish we could measure noise figure and say, right, that's it. We can move on to the next thing now. But the way human nature works, if you have something that you wish you didn't know about, then... Was there something, David?
Oh, sure.
Oh, all right. Anyway, yeah. So the alternative title is a memory refresh. I'm going to move through this quite quickly. We're all fairly familiar with the Y factor measurement that's used in most equipment. You have the noise source, the noise figure analyzer. Between them, you put the device under test. You begin by connecting the noise source directly to the noise figure analyzer for calibration, and then you move on to your measurement with the DUT in place. Looking at the noise figure analyzer more carefully, what we have is a precision noise power measuring receiver, and David will tell you more than you would ever want to know about this, followed by some computations which take care of the calibration and calculation of the two things you usually want to measure, either the noise temperature or the noise figure of the DUT. Choose your units. That's your choice. And the gain of the DUT. And finally, it's displayed. The problems, therefore, are these. In the hardware, we have problems. There are what I've called numerical problems in the computations. And finally, of course, there are credibility problems in the readout. So we're going to take a simplified example and try to show you in a more visual way than we've been able to do in the proceedings how the errors arise. So for a simplified example, the noise figure of the analyzer is 0, and that means we don't need a calibration step. We just connect everything up and go. Okay, noise figure is about signal-to-noise ratios at input and output. So we're comparing measured noise outputs against noise input power, and that's most conveniently expressed in Kelvin in equivalent noise temperature. On the output side, it doesn't really matter. It's arbitrary instrument units. But both of these are linear scales, and both of these, when we start to populate this diagram, everything has been done using realistic numbers. Okay, so we know we connect the noise source, which is switched off, and that gives us what we call T-cold as the input power, and we measure a certain amount of output power there. We turn the noise source on, and that's T-hot, about 1600 K for a typical 5 dB ENR source, and we measure a larger amount of output power. The method is then that we join those two by a straight line, the slope of which, taking into account the instrument factors, gives us the gain of the DUT. To get the noise figure, we then have to extend that line downward. Imagine if you had a noise source that you could plug into the front of the DUT, which had a noise temperature of 0 Kelvin. It generates no noise power at all. Then what you've measured there is the DUT's own output noise. In order to get at the noise temperature of the DUT itself, we extrapolate that even further. Now, don't worry about the negative temperature axis there because, okay, there's a minus sign there, there's a minus sign there, no laws of physics are being violated. But here is your problem. You're trying to measure this tiny thing here is what you're trying to measure by joining up two measurements that have been made at different levels. Furthermore, these are noise, so every measurement point you take is a fuzzy one. And you hope, or you pretend, that it's okay to draw a straight line. This is where the trouble starts. So it's a ghastly, it's an awful measurement technique to measure something so tiny, so far away from the actual quantities that you can physically measure. Right, so here are some of the problems. Well, okay, it's the best technique we have, or maybe it is. If we have time, we'll come back to that. Right, so let's look at some of the errors. The first error I'd like you to think about is the error in T-cold. In other words, you've got that point wrong. If you have that point wrong because you haven't bothered to measure the physical temperature of the noise source, but you just guessed at it, then that moves. It also changes T-hot if you because of the nature of the formula. And what happens then is that that small error goes degree for degree.
6 Kelvin will give you 0.1 dB error in your noise figure result.
Yeah, and that's a completely avoidable error. That error is almost at the category of user error, finger trouble. Next one, one of the two big ones is the excess noise ratio of the source. And that affects mostly T-hot. And what happens there, if you get the ENR wrong, T-cold stays where it is, and that happens. One of the things that also affects is the measurement of the gain of the DUT. So ENR errors are really quite serious. And the problem is money cannot buy an ENR calibration uncertainty better than 0.2 dB. So you can see the problem immediately. We're trying to measure noise figures that are getting lower and lower, and maybe even sub 0.1 dB. We don't know, but there is an uncertainty of 0.2 dB on anything we measure. And that is even if we don't make any further mistakes. Thinking of further mistakes, there's the possibility of a gain error, nonlinearity in the noise figure analyzer. And I won't dwell on this. This isn't a big one, usually. But that does that. And every time we're doing that, you can see DUT is simply we're getting it wrong. So let's move on to the other. The other really big one is the gain change in the DUT between having a cold noise source connected to it and having a hot noise source connected to it. That means that those two measurements are both wrong, and furthermore, it isn't valid anymore to join those 2 points by a straight line. If you decide that you will do that you will use a straight line, then the problem then turns into points A and B moving in a complicated dance relative to each other. And you then get some rather interesting problems. Okay. That one, TDUT, is apparently getting bigger. Okay. That's the correct value. It's getting smaller. There is absolutely nothing to stop that happening. And then we're in big trouble down there because we seem to have a negative noise figure. That is a physically... It obviously isn't true, but it is correct that a noise figure analyzer can indicate a negative noise figure because of that error. That error is real and true, and the noise figure analyzer ought to indicate it. Now, here's a problem. This is one of the buried bodies. I don't think David's exactly quite sure where the body parts are of this one. But
we scattered them widely.
Yeah. The various companies and various instruments have decided that it would be completely unacceptable for their instrument to indicate something which appears to be physically impossible. So they fix it. They flip the sign or something like that, which has the unfortunate effect that the tail of measurements that are going into the negative region then get overlaid onto the low and positive region, and there goes all your noise statistics. So be aware that under some circumstances, and we're not quite clear what they are, to be honest, some readouts can tell deliberate lies. If you want to know about the pressures of that kind of thing on designers, then talk to David at length in the bar, or listen to David at length in the bar. Right, moving on. The gain change in the DUT depends on three things. First of all, the noise source and the change in output reflection coefficient. It's well known that a 5 dB ENR source is better in this respect than a 15 dB source because of the extra 10 dB of attenuation, which improves the return loss by 20. We seem to hold that in our minds. This is the more slippery one, that there is a problem with some DUTs. Poor input matching makes this gain-change error much, much more important, to the extent that some preamps then become unmeasurable. The third thing is what happens when we tune the DUT input and all these things begin to interact. And the problem is the errors can go positive or negative, and you don't know how much. It's literally unknowable. Analysed by Reiner in 1988, I think this is partly what kind of puts people off. This is similar to one of the graphs that Reiner drew. It's computed for a 5 dB ENR source, and it means that when you start to tune your preamp, the indicated value is not the minimum. What you're tuning is mostly the errors. And this, I think, is part of the reason why some preamps at different measurement places end up giving really quite similar results, because they are the same noise source, the same model of noise source, with the same physical internal dimensions. So the phase angle is the same, and if you're there, then you can go somewhere else with a different noise source, and quite possibly you will still be there, indicating a low noise figure. So that's the difference. The 1980s style of LNA, which was what prompted Reiner to do this work in the first place, versus a more modern one with better input matching. And what's happened in the meantime since the 1980s is noise figures in general, we believe, have come down, and this error then becomes quite important. So it needs something with good input matching to push that error down below the threshold of concern again. So just to repeat that, it really is bad. We wish there was a better way. But what we have to do, I think, is whenever we quote a noise figure, we got to grow up and say, this is a noise figure of so-and-so with an uncertainty of such and such. So please, if somebody quotes you a noise figure, you say, and with an uncertainty of, and try to embarrass people into finding out about this. Agilent's online uncertainty calculator, we recommend this one, the online JavaScript version, because it's got a lot of good default values. So you select 346B for the noise source, and it picks up those values automatically instead of you having to make a decision. Later, you can come in and refine those if you wish. Similarly, with the instrument defaults, 8970B is the latest model that they allow you to have, but you can put other figures in there if you want. And then you type in the numbers you've just measured for the noise figure, and I'm standardizing here on 0.3 and 30 dB. And here, these are numbers that you can measure or guess at or hope for. And so we'll look at something with a reasonable input match. Minus 10 means it's a return loss in dB. Click tabular results, and you see that, which gives you the uncertainty, the total root sum of squares uncertainty of 0.293 dB. So you've measured 0.3 dB with an uncertainty of, well, 0.3. Okay, of which a large chunk of that is the ENR uncertainty of the source. And, yep, as I said earlier, money can't buy you anything much better than that because of the journey that the calibration has to make step by step from a national standards lab. The next big uncertainty is that input mismatch. And again, even with a reasonably good match, that's quite a large contribution to the uncertainty. Remember that this is root sum of squares, so those numbers don't add up to that. Don't worry, Agilent did get it right. I checked. So that is your result in the end. That's the true result, and are we worried yet? We should be. Right, let's do it again for a poor input match, and that really blows it. What it means is a preamp with a poor input match, no matter how good it is, we aren't able to measure it with any certainty. This is purely a matter of personal choice, but I don't care how good it is. I will never feel easy with something that which has so much uncertainty hanging about it. Okay, so final point, of course, is it's the input match, or lack of, that's causing the problem. So the conclusions before I hand over to David is that the uncertainties can be larger than the thing that you're trying to measure. And I think this means that for us, the Y-factor method is coming to the end of the road. We need to find something better. Now, David will talk about some of the techniques that he looked at before they decided to go with Y-factor again for the new range of Agilent analyzers. We need to find something better, and my feeling personally is that we need to avoid preamp designs that make the uncertainties worse than they absolutely need to be. But most of all, as years go by, as another 20 years go by, and I don't think, guys, it's quite as bad as it looks. There's numbers of us older guys have been saying, ooh, too many old people. I think most of you can be here in 20 years. Yeah, but please don't come back to somebody giving this lecture. Yeah, this time let's try to remember it, and this time let's be the core of people who pass it on and spread it out into the rest of amateur radio. That's all I ask. That's us. Okay. David.
Yeah. So G9QRN makes preamplifiers, and he sells them, and he claims a noise figure of something realistically 0.06, 0.08 dBs, something like that. They might even do that. The whole point is that we don't actually know. He can't prove that his noise sources reach that noise figure level of performance. I can't prove that they don't. What I can prove is that he can't prove it. That's the situation we're in. I had a word with Jan earlier about what sort of language and words I could use. So all I can tell you is that noise figure measurements is very, very bad. I'm the person that describes the F connector as F stands for awful. But it's like going to a sports car meeting, lots of people all going down a runway, measuring their 0 to 60 times, and proving that if you give enough money to Ferrari, Porsche, Maserati, you can get there in under 3 seconds. And I walk in and say that the most accurate stopwatch they can get is only guaranteed to plus or minus 15 seconds. And that's the sort of scale we're at. So Ian's passed over to me. Questions, please. Yeah. Sorry, I need to catch you out. By the way, if anybody wants, there's a 346B with an attenuator stuck on the end, which is one of the best things to do to it, short of changing it for 346A. And that is the original lab prototype of the smart noise sources. If you want to pass it round or have a look at it afterwards. No, okay. Can't I have the British Karate Club search everyone afterwards?
I'd just like to point out that one of the worst things that we do as a large group of VHF interested people is have at our regional meetings frequently noise figure measuring contests in which you have a lot of preamps and some guys that with good instruments make measurements, and then there's a table plotted with the winner and the second place and so forth, and the first 10 may be within plus or minus 0.2 dB. They're indistinguishable, in fact, although somebody wins a prize, and that's silly. Those numbers should all be published with plus or minus something after it, and then you can see how much they're really different, or not, as the case may be.
Would you please put your hand on your heart and this stack of religious books and swear that this was not a pre-made question and pre-arranged? Thank you. Right, what happens about that is Ian pointed me at a number of things, and I was doing a Victor Meldrew. It's not possible. They couldn't be. No. And one of the things he pointed me at was a table of just that from a predecessor meeting of this held in Thorn. And there's a whole collection of different call signs. They brought their noise figure measurement gear along. They brought a lot of preamps along together, a sort of thing that the professionals never got organised enough to do. That's what radio amateurs do well. We deploy lots of people doing things that the professionals couldn't afford to think about the budget for. And you have a look at it, and you pick one character, any character out of there, and he's brought his preamp along and his noise figure set. You look at the results of his preamp, and it gives you its best results on his noise figure set. You look at another guy, his preamp, where does he get his best noise figure? On his noise figure set. It's a marvellous proof, you could almost do a PhD in it, that there's a strong correlation, and that it shows that these preamplifiers are not being tuned for absolute minimum real noise figure. They're being optimized for the lowest displayed value on that specific set of instruments. And it shows you that there are variations going on.
You're absolutely right. There's a lot of factors that enter into this. One thing, though, it's not as bad in these contests as it seems, because you cannot make comparisons from one contest to another, but at least you know that the ENR of the instrument that is used is the same in everyone. You get into the match errors, and people tune their preamps for the match errors. I wanted to address, and I thought Joe was going to go that way as a radio astronomer, because us hams are not as bad as it often is taken on. And there's been some really serious work to go beyond what happens when you use a noise source. And I think it's pretty well accepted by, and I know Sam certainly has looked this way. Shake your head, Sam, hopefully, beyond what happens with a noise source. There's been a lot of work to correlate these measurements to measurements made with a calibrated antenna using external, when I say external, extraterrestrial type sources to work backwards and be able to correlate the measurements of the noise figures we're doing. So it's not as good as many of us think, but it's not as bad as your first impression is.
I agree with that
you put these factors together.
Yeah, I've been carefully using phrases about the bounds on the uncertainty. I'm not saying, you've got a noise figure of this much in your amplifier. You've then got an error of a certain amount, and then the other thing that's floating around is you've got some bounds that can be mathematically and through the metrology of the passage of everything from a national physical laboratory through to yourself, you'll have bounds of doubt and uncertainty done by, it's essentially RSS addition of the factors. If you want to look it up, it's tag 4 methodology that's used in most of these things. If you have a noise source, this is one of the very worst. It's a 15 dB one for starters. I picked it up in an amateur radio rally for 25 quid, which I think is a bit of a bargain a while ago. And instead of having a table of numbers on it, it's got a graph with little dots put on it, and you can almost read it to about 0.1 of a dB. Fairly awful. But if you get one of these calibrated, you get a sheet of paper. And compared to the proper printed numeral labels, you actually get serious statements with more decimal places. You get a statement for each of the standard frequencies, 10 meg, 100, 1 gig, and then round numbers of gigs, telling you what the uncertainty on the ENR is. And you'll find the uncertainty on each frequency is different. If you take that back to where it got calibrated against another higher echelon noise source and take it back, we changed over from using NIST as a standard to NPL because NPL had backed down their statistical accuracy estimates for their system because due to cuts, I understand, a roof had collapsed under a lot of rain and it had destroyed quite a bit of their equipment and they'd had to rebuild it, get it going, get it fixed, put things back together again. And they were slowly trying to build up statistically provable confidence in the results from it. So we shifted the calibration of 346s and the smart noise sources from then onto NPL in London. There was one other national standards lab that was actually offering even tighter bounds than they were, but they were so tight that we honestly didn't believe it. And it wasn't a case of being Britocentric or something like that. NPL offered us the best figures that weren't unbelievable. And we went there. But if you go back, you'll probably find that there's a separate piece of apparatus for each of these individual frequencies. So if you want it calibrating smack in an amateur band and not doing an interpolation and making an extra error allowance in the budget for that, you send it back to them. What do you think they're going to do? They're going to do an interpolation for you. If you pay them an immense amount of money, they might make a whole new hot and cold resistor pair for 432 megahertz or 1296. But it still won't be very good because the ones on the standard round number frequencies, there are the other national standard lab and they keep calibrating noise sources and passing them round. The noise sources themselves are actually pretty stable. You do get a change in impedance on the output between diode on, diode off, even with the 6 dB ones, and that's probably their Achilles heel. But the big problem is if you want to know what your noise figure is that you can actually prove it to be, if you were trying to sell it as a product and guarantee a specification, then it's the number of dBs of doubt and uncertainty from the national laboratories that trickle all the way through the system, getting a little bit worse all the way along, but you people are making preamplifiers which are significantly, an order of magnitude better than the best accuracy that the national laboratories can guarantee.
Sorry, Dave, we have to go to the last question.
Sorry.
Yeah, I wanted to, one thing that's important is that we don't get crazy about what our absolute noise figures are, because when you put this on an antenna, the antenna has an impedance. And so you're interested in what your overall performance is with the antenna. We can get into a lot of, because there's been a lot of papers and discussions in the amateur about tuning on the antenna if you really want to get that last little tenth of it. I had one comment. Have you guys looked at the same thing that people do with loads? Because the impedance is a big problem, and there's not a good solution to that of using a line stretcher. As hams, we have done this in the past of this is adjusting the, just like you have a load, and I better get out of here.
Yeah. Yeah, we've done that. If you've got a noise figure set up and you want to give it a really hard workout, try measuring the noise figure of an attenuator, and then a bigger attenuator and a bigger attenuator. That's a fairly good check as to whether it's working particularly well. And if you change the temperature of the attenuator, you should be able to calculate that effect. There was a question?
Yes, we currently have a lad producing some preamps with some absolutely incredibly claimed noise figures. But then when you put them on a spectrum analyzer, you're finding they're all oscillating. Oh. What is happening in a noise figure meter to allow a power oscillator to have such an incredible noise figure?
Okay, something says end, but yeah, I see that. There are preamplifiers around with very, very high Q, sharply tuned inputs. These do several bad things. First of all, they tend to present impedances to the device at other frequencies that can get them rather frolicsome, and they will start oscillating. The other thing is they give you an astronomically steep change of gain versus impedance, particularly in the point where the optimum noise factor lies. The best noise factor is at a different place on the Smith chart to where the best gain is. So the gain is changing fast, and it deliberately makes worse.